All right, so we're working in section 3.2. These are called sum and difference formulas. There's a bunch of formulas as we continue to work through this whole chapter, but nothing else moving from here forward you are required to memorize, okay? So as we're taking a look at these, some of them set themselves up. They're very obviously going to use one of these formulas, and some of them are not so obviously going to be using a certain formula. So we're going to take a look at both of those kinds today. So starting with, we're going to take a look at sum and difference identities. So these are the identities for today's discussion. And they're presented a little bit more, a little bit differently on your handout because the screen size and so forth. But they're very similar, right? So we have cosine of alpha plus beta. And then this is the cosine of alpha, cosine beta, minus sine alpha, sine beta. Remember, alpha and beta are just angle measures. And then we have one for the difference of the cosines. We have one for the summation of sines, sine of alpha plus beta. And then what you see differently than the one before is that we have sine and cosine of each of the individual ones. Then you have the sine of the difference. Okay, they look very similar to the sine of the sum. And then our tangent of alpha plus beta looks way different than the sines and the cosines. And while it's true that you can use this tangent formula, and there may be opportunities where that makes really good sense to do so, you can also have the sine and the cosine values and simply do the division, right, sine over cosine to find tangent. And sometimes that's easier to do. So everything that we've been working with about quotient identities and reciprocal identities, all that stuff is still applicable. And it may be more preferable in certain situations to use those. So just because we've got new formulas doesn't mean they have to be used on every single problem. Shake your head if you're cool with that. Okay, so if you're looking at that and you're going, I think it would be easier to do such and such, feel free to do that at your seat if you'd like. We will get the same answers at the end if we've both done it correctly. Okay, so keep that in mind. The first one we're going to take a look at very clearly uses these identities. As you're looking at that, you see cosine and you see two items that are subtracted. If you tried to simplify the subtraction of 2 pi over 3 and pi over 6, you may or may not get a nice value. Okay, if you did, that'd be great. But a lot of these are such that you don't get a very nice value if you subtract. It doesn't end up giving you something that you know a unit circle value for. And that's why the sum and difference identities are there. They're there to allow us to use previously learned information, right? If we can do new pieces of information that allow us to fall back on things we've already learned, we're saving ourselves a whole lot of work. And that's the goal. So this one specifically even tells us what we're supposed to do. It says that we're supposed to use the formula for the cosine of the sum of two angles. And it should say sum or difference of two angles. That's a little bit of a typo because this one's clearly a difference one. So if you go back up to the screen before, right, this is the formula that we want to be able to use because we have a cosine and we have a difference. In this formula, we have got the cosine of each of them at the beginning, the two different angles, and then there's addition, and then we have the sine of the two angles. So we're going to rewrite this as the cosine of 2 pi over 3 and the cosine of pi over 6. And then it's the sum, looking at that formula, and then it's the sine of 2 pi over 3 and the cosine of 2 pi over 6. My handwriting is going to be a little bit less clean today. I apologize for that, but apparently my daughter used the eye pen a little too much when we were out of town, and it is now dead. So we're going to make do. Alrighty, so each one of these values, the 2 pi and the pi over 6, are on the unit circle, which means, again, as long as you remember your unit circle stuff that we've worked so hard to do, we know we can find all of these values. Okay, so whether you want to grab your unit circle out as a refresher or whether you want to just remember what the details were, thinking about where 2 pi over 3 is, what is the cosine value at 2 pi over 3? I'll sketch a little bit of a picture just to remind us because it's been, unfortunately, a few days since we've been in class together. So 2 pi over 3 would be in this quadrant over here. Are we closer to the y-axis or the x-axis at 2 pi over 3? The y, very good. So we're up here. So we're looking at the cosine value, which is the x value at that point. What is the cosine value at 2 pi over 3? It's negative 1/2. Very good. And we're going to use that 2 pi over 3 in a moment. The other angle is pi over 6. So if we're looking at pi over 6, we're in quadrant 1. Changing the colors out here. Wow, that wasn't where I wanted it to be at all. Let's try again. And it's closest to the x-axis on this one. And now it says the cosine value of that location. So what is the cosine value at pi over 6? Square root 3 over 2. And then to this, we're going to add. Okay, so what would the sine value at that first 2 pi over 3 location be? Yep, that one's square root 3 over 2. And then what? Oh, I don't know why that says 2 pi over 6. That just should have said pi over 6. No wonder you guys are looking at me funny. Let's take that 2 out. How about pi over 6? Yes, 2 typos. Thank you. Okay, does it look okay now? Thank you. Sorry about that. I think I've told you this before, but I zoom in and zoom out all the time, and so I lose pieces of my screen. So I'm sorry when I do that. Just let me know, and we'll get it fixed. All right, let's try again then. Sine then of pi over 6. So what is the sine value at pi over 6? It's 1/2. Yeah. All right, so we're going to actually calculate this. So if we take negative 1/2 times square root 3 over 2, what are we going to get? Y'all are really overthinking this. We just multiply across the top. Negative square root 3 over 4. You got it. All right, same thing on the second one. Multiply across the top and across the bottom. Yeah. So what happens on this one? It cancels out. It gives us 0. That is very atypical. That's not what you're going to see normally. So what I'd like for you to do then, to just check this, because this will actually work, even if this had been a square root 3 over 6 value or something like that, you gotten something weird, right? You can check to make sure that the decimal that you get matches with the decimal that this would represent. So let's just check that real quick so you can see how that would work. So if you grab your calculator, notice this problem's in radians, so make sure you're in radian mode if you're doing this. And you can actually type in cosine, and you can put in the parentheses 2 pi over 3 minus pi over 6, and press enter. And it will give you, in this case, or it should give you a 0. In general, it'll give you some decimal expansion, right? Some expression that's not very exact, but you'd be able to take the answer that you got, turn it into a decimal, and you could at least check that they match. Okay? Does that make sense? Okay? So please do not think they're going to all become nice values. Usually they don't become nice values. Usually they're really ugly at the end. Okay, let's take another look at a different type of one. So I've tried to hit on the different kind of directions you'll see so you can see how they work. So on this one, you would actually, if you were given this on a quiz, right, be asked to write all that out, be asked to find the individual values, and then be asked to consolidate at the end. It would look much like this. Your work should look like this. This one asks for this done in a little bit different way. Now, if you take a look, skip the directions just for a minute, and look at the expression they give you, they don't give you the left-hand side of the expression like the last problem did, right? They give you the right-hand side of the expression. In addition, if you look at the values that they give you, these are not nice values. 50 and 5 do not work well on a unit circle, right? Those are not degree measures that you have memorized anything about. So what you want to think about as you're taking a look at this is, can I add them or subtract them and get a nice value? Well, if I add them and get 55, that's not very nice. If I subtract them, though, what would I get? 45, and that would be a really nice value. So that's what the motivation for these problems are, is we're turning them into something we can use, right? So it says, first, the directions say, consider the following to be the right side of the formula for cosine A minus B. They shouldn't really need to tell you that, right? Just like we said, it looks like it. And so we're going to look back at that same cosine of alpha minus beta that we saw before, that I've underlined here. And we're going to notice, and it says plus. So notice that if I have the subtraction here, it actually becomes an addition over here, right? And that's the addition that we have in our problem. So if we're going backwards, we end up doing the subtraction that we discussed, 50 minus 5. So we're going to rewrite this then, very nicely, part A, as, it says first, identify alpha and beta. So let's do them in steps in order. So alpha is what? 50, and beta is 5. Part B says to write the expression of the cosine of the angle. That's the one I was trying to jump to. So if we move from the right to the left in this equation up here, we're taking the addition of these 4 pieces and we're merging them backwards to the subtraction of the angles. So I'm going to write it out a couple of ways just to make sure you're seeing it. This is 50 minus 5. what they're wanting you to write down at the end, of course, is that this is the cosine of 45 degrees. Okay? And then part C says to find the value of the expression. So, what is the cosine of 45 degrees? So, unit circle value. Yeah, it's square root 2 over 2. Now, just for good measure, and we're going to, if we have time, which I think we will, we're going to do this on each of our problems that it applies to. I'd like for you to put into your calculator. Now, you need to be in degree mode, because this is in degrees, so switch it out if you've got it in radians from the last problem. In degree mode, I'd like for you to type in cosine 50, cosine 5, plus sine 50, sine 5. It's going to give you an ugly decimal, just like I predicted from the last problem. Ugly decimal is going to come. And you can press enter and you can check that ugly decimal. And then in the next line, you can type in square root 2 over 2. And you can see that the decimal expansions match. Just the original problem that they gave you. Yeah, if you just put in this original piece that they gave you up here, right there, and you put in this one right here to compare them, they should give you the same decimal expansion. Yeah, 0.707 and some change after that, right? Yeah. So it should both give you the same decimal expansions, and you can check your work that way. So I don't mention this because I want you to sort of have a workaround in my math lab to getting the right answers, because if that's how you use the information that I've given you, it's not going to do you very well when you get to a quiz or a test. But I hope that you use that information so that when you get to the quiz or the test, you have a way to check the work that you've been doing and make sure that it really was the answer that you were supposed to get. Because if you accidentally used addition instead of subtraction somewhere, and you checked the value from the beginning and the value from end and saw that they didn't match, you would know, I did something wrong. I need to go back and check that formula I used and make sure I used it right. Does that make sense? Okay, so let's take a look at some more. So these don't have near as much directions to them, these next couple. They just simply tell us to find the exact value of the expression. So these are a little bit more authentic, whereas these were directly telling you which formula to use, right? These are asking you to figure out a formula on your own based on the formulas you were given. So if you'll notice, this one has sine, cosine, and then cosine, sine, and it has subtraction in the middle, right? So we're going to flip back over here together. We need to have one that says sine, cosine, cosine, sine with subtraction in the middle. Do you see which one that might be? Okay, so if we go down my list and we sort of go in order 1 through 6, which one is it? It's number 4. I've got sine, cosine, cosine, sine, subtraction in the middle. This is the formula that matches the form of the problem I'm working with. And what it says I need to do is to take the sine of the two angles subtracted. First angle minus second angle. So over here, I'm going to have the sine, the first angle, pi over 12, minus the second angle, 5 pi over 12. It is really tempting to flip the subtraction here around, because clearly pi over 12 is smaller than 5 pi over 12, right? 1/12 is smaller than 5/12. So you don't want to subtract them in the reverse order here, and there's a good reason. You will end up with the wrong answer at the end. It'll actually be really close, but you're actually going to end up with a slightly wrong answer. So make sure you put them in the right order. All right, so this is fraction subtraction now. So if I have pi over 12 minus 5 pi over 12, what will that give me? The denominators match. I mean, like, that's good news already. Yeah, so it'd be negative 4 pi over 12. And then that will reduce, right? Still be negative, but what will the 4 pi over 12 reduce to? Pi over 3. Now you can use this as is from the unit circle if you'd like. You can also, though, use even and odd identities. There's a negative inside with the angle. What happens for sine with a negative angle inside? Does the negative come out in front, or does the negative disappear? Those are the two options. It comes out in front. For sine and tangent, the negative comes out in front. For cosine, it disappears. So I can rewrite this as negative and then the sine of pi over 3. Okay, you don't have to do that on this problem. You can do this on the unit circle and go down into the fourth quadrant in a negative. That's fine if you want to do it that way. But you also could do it with even odd identities. don't think it asks you to. I don't think it's going to ask you to do it step by step. I think you're far more likely to see something where it wants you to change it into some version of either this or this, and then to give the final answer. I don't think it's going to have you do all the steps in between. So yeah. What's sine of pi over 3? Yeah, it's square root 3 over 2. Square root 3 over 2. And the sine of negative pi over 3 is also negative square root 3 over 2, if you do it from that perspective, of course. Okay. I actually think this kind of problem, compared to what we're about to do in number 4, is the easier version. You're identifying the sines and the cosines, the addition or subtraction. You can find the formula over here. Whoops, sorry, one more there. Pretty straightforward of what you need to do. Okay? It's a pretty straightforward process. Number 4 is a little trickier. Because on number 4, there's no addition or subtraction listed. It does have just cosine. But what we want to do is we want to break that 105 apart into either the addition of something that's helpful or the subtraction of something that's helpful. Okay? So we would like to take 105, and I'm not doing this for factoring. Like, this is not like a factor tree kind of thing from algebra. I want to find two numbers that either add or subtract to 105 that are nice ones, like ones we know things about from the unit circle. Right, so for example, 105 are not helpful here. They add to 105, but they don't do any good for me because I don't know an angle measure, what the sine of 105 is, or I don't know that. Any thoughts on what you could do for 105? 45 and 60. Is that okay? Yeah, and it's addition, right? So 45 plus 60 will be what we would need here. So I can rewrite this as the cosine, and you can put the 45 and the 60 in whichever order. It won't matter, okay? So pick your favorite, doesn't matter. This is a cosine of 45 degrees plus 60 degrees. Once it's in that form, again, it looks just like something over here. Maybe not too far. So this said cosine, and it said addition, which means we're up here now, right? So this is where we are at the moment. It says that we're going to do the cosine of each one of them with the alpha and the beta, right, the angle measures. And then we're going to subtract that and do the sine of each one of them. Okay, so we've got 45s and 60s. The order didn't matter. We'll go with whatever order we wrote down, 45 and then 60. So this is the cosine of 45 and the cosine of 60. And then I think it was subtraction, was it? Yep, good. And then I have the sine of the 45 and the sine of the 60. Oh, we didn't try that on the last one. We'll go back and check our work on the last one in just a second. I forgot that part. All right, cosine of 45. What is the cosine of 45? Good, square root 2 over 2. What is the cosine of 60? That's 1/2. All right, sine of 45? Square root 2 over 2. And then the sine of 60? Square root 3 over 2. Okay, everybody good so far? This one's definitely going to be messier looking at the end than the others that we've seen. So we go straight across and multiplying. This is square root 2 on top and 4 on bottom. What happens on the top of the next one when I multiply square root of 2 and square root of 3? Do you remember from any algebra stuff you've done before? Yeah, because they're both underneath the radical, we can multiply them, and they are square root of 6, and the denominator is still a 2. Sorry, not a 2, a 4, I meant to say, just like the last one. Okay, is everybody good? Because the denominators match, I can merge them together with the same denominator, a single denominator. And while it's true that I can multiply the values underneath the radicals, I can't do that with addition and subtraction. So the best solution that I can leave it in is square root 2 minus square root 6. There's not a cleaner version of that. Okay? Don't want radicals on bottom, but we don't have any radicals on bottom, so that's okay. Let's check this one, because this one's certainly going to give you an interesting decimal that you've not seen before kind of thing. So clearly easy enough to put in the cosine of 105. Make sure you're in degrees, because we've been moving back and forth. And then put in the square root of 2 minus the square root of 6. Make sure that you have the entire expression divided by 4, not just the square root of 6 divided by 4. What you're checking for is, do the decimals match, right? And if we've done it correctly, they should. Okay, Shaylin's nodding. Yours matched. Wonderful. Did anybody else check theirs? Yes, Beck's match. Okay, so I think we're good, right? We got the pieces in. We got them in the right order. Generally speaking, you can't really put in cosine 105 and then tell your calculator to put it back into radical form when you've got a square root 2 minus a square root of 6 over 4. Your calculators aren't very friendly with some of that stuff. Sometimes some calculators will put something back into a single square root, like a square root 3 over 2 form. The TI-84s don't, if you've got one of those, but some of the Casios do. But I don't think even the Casio will put this back into a nice form for you, just so you know. Let's check the last one since we skipped that one. I apologize. Make sure you're in radian mode because this one's got lots of radians going on. I think this one might be more work to put into the calculator than to actually do the work we did by hand because it's so messy from the beginning with all the pi's and stuff involved. But if you put this piece right here in, right, sine pi over 12, cosine 5 pi over 12, minus cosine pi over 12, sine 5 pi over 12. Be careful with your parentheses because there's a lot going on in that problem. And then also put in the negative square root 3 over 2. We should get the same expression when we're done. This one's taking a minute to put it in, isn't it? Yeah. This might be one of those ones you star on the quiz or the test and say, I'll come back if I have time to put this one in because it's going to take a minute. Whereas the other ones are quicker. Yeah. Did you get it to work? Okay, so Lydia's got hers to work. Did yours work, Reese? Excellent. So I think we got 2, so I think we're good. Okay. So I prefaced all of what we were starting with today that some of the things we were going to do are going to look like section 3.1 and some of them were not. Everything we've done so far does not look like section 3.1. Nod your head. It didn't look anything like 3.1. 3.1 when we want the left-hand side to equal the right-hand side. This is actually numerical values. It's using the unit circle. It's allowing us to find values that we would not otherwise know an exact value for. We could get an approximation, right? Cosine 105, my calculator can tell me an approximation, but I can't get an exact measurement. Now, some of you are thinking, well, do I really need an exact measurement? Well, sometimes you do, right? There are places and things for which you want very exact measurements, right? If you've had any experience with watching any of the movies about spaceships, like, when they go and they do stuff, like out, like the shuttles and stuff like that, they need exact measurements. Small things going wrong makes big things go wrong in space, right? Like all I know that is from movies, but it's true, right? So there are times when exact measurements are absolutely crucial, okay? So this is allowing us to have another avenue to find exact measurements. The last couple of examples I have are actually going to mirror more like what we did in section 3.1, okay? Verifying identities. So this is an identity. The sine of pi minus theta is equal to the sine of theta. In fact, I can't remember if it's on this sheet or not. It's not on this one. I think this is one of our cofunction identities. I don't even think it's on the sheets front and back. But this is one of our identities, and we're going to verify that it actually works. Now, if you look at the left-hand side in and of itself, it looks like what we've been doing, right? It's got two angles, and they're subtracted. Okay? So I'm trying to match it up, like when I'm thinking about this sheet, right? The sheet of all these identities, and we're going to have more and more build on this. I want to find something that looks like the sign of two angles subtracted on here. So as we work through and we get to sum and products and half angles, and we get over here to all these different things, we've got more and more and more things to check. But what we're looking for is something that looks just like this. And of course, since we're in 3.2, we know which ones we're using because we only have this one block, right, in our notes. It is the first set, and so we want the sign of angles subtracted. So over here, the sign of angles subtracted is this number 4 one that we had done before. I need to clean these off. So it's this one. I've got the sign of alpha minus beta. This is the one I'm going to be using. Now, in the case that we're working with right here, my alpha is pi, right? I'm going to write it in on here just to identify it. And my beta is theta. That's not exact numbers. I mean, pi is, but theta is arbitrary. Okay, so we're not going to get a number value when we're done with this one. But I'm going to be able to put the pi's in for all of the alphas and the thetas for all of the betas. So it'll look like that. I'm going to flip my screen in just a second, but is that okay? Okay, so let's come over here. One more. And we're going to rewrite, and we're working with just the left-hand side. Why would we work with just the left-hand side on this one anyway? Why would working with the right-hand side not be a good place to start on this particular problem? It's very clean and simple, and there's nothing we can do to make it any, cleaner, right? It's as simplified as it gets. So there's often a place to start that's more helpful than the other. Not always, but often. So on this one then, we have our sine. We've got the pi. And then over on the other screen, we saw cosine of theta minus, and then I've got the cosine of theta. I'm sorry, cosine of pi. And sine of theta. And I'm not manipulating the right-hand side, okay? The right-hand side is going to stay the same the entire time. At the end, hopefully, the left-hand side also says sine theta. Now, theta is arbitrary, but pi is not, right? Where is pi on the unit circle? Yeah, it's on the negative y-axis, right? Okay, so on the negative y-axis, I'll just sketch that in real quick. On our negative y-axis at pi, right over here, what is the sine value? It's 0. Sine measures how far up and down from the x-axis you go. It's 0. So I have 0 times the cosine of theta. What is the cosine value over there? It's -1, right? -1 measures how far left and right from the y-axis we go. It's -1. So notice what happens in the first piece, right? I have 0 times cosine of theta. What does that give me? That's 0. Okay, so I'm going to belabor the point for a moment and actually write it in. You're welcome to not if you don't want. The next one, actually, I have a negative times a negative. It's a positive, right? You bet. So now I have a positive, and 1 times sine would be sine of theta. And clearly, if I add 0 to it, whether I wrote it in that step like I did or not, I get sine of theta. It matches the sine of theta on the other side. When I'm done, they check out. Your work needs to very clearly indicate that you're moving down one side to equal the other. Some of you really like to work from left to right on your paper. There's probably 4 of you in here. That's my guess. Okay, some people like to work left to right. One of my kids does. Some people like to work top to bottom, and I've got kids in my house that do, okay? It's probably the way that our brains are wired. It's probably more that than anything else. But for these problems, you really need to work down the paper, because otherwise, I don't know but what you've accidentally started working on the other side of the equation. I'm liable to take points off because I can't tell for sure. And I really need to see that you're only working on one side. Okay? And I know I probably said this in the video for 3.1, but let me remind you why. We're trying to establish or verify or show that that equal sign there is appropriate. We cannot assume that the equal sign is appropriate when we're trying to prove that it is. Right? This is like when I ask my kid, well, why don't you want to go out to dinner with all these people tonight? Because I just don't want to go. That's not really an answer, right? Why are these two things equal? Well, they just are equal. We got to actually show that the two sides are equal, so we cannot use any of the facts of equality to do that. Cool? All right, we've got one more. I would contend that there's not a very strong, compelling reason to work with one side of this over the other side. Both sides look terrible, don't they? I mean, like legit. They look awful, right? You can work with either side to make it work. And you will get the right answer, okay? So it's okay if you choose to work with the left. It's okay if you choose to work with the right. I'm going to suggest that we're going to work with the right just because my notes match that. And that way, if I make a mistake, I'll know quickly that I've made the mistake and I won't lead you guys astray. But I don't want you to think that that means that it has to be the right-hand side to work with on this one. The left-hand side would work as well, okay? So I'm going to start with the right-hand side. And instead of using any of the theorems in this section, I'm going to use a theorem, not a theorem, but an identity rather, that we've used before. Tangent. What's the quotient identity for tangent? The one you've already memorized from way back when. It's sine over cosine. And we're going to write that down for these, okay? It's a nice way to get sine involved because I don't really have, if you take a look back over here at these options, even though there's a tangent down here at the bottom, it doesn't look like the tangents that are on the other side of that equation, does it? Its form does not perfectly match up. So going through to this, if I'm going to start with the right-hand side, going through and using tangent on it would not be helpful. If I were using the left-hand side, can you see how these identities would be very helpful? Yeah? It was the sine of alpha plus beta and the sine of alpha minus beta. We have formulas straight for those, so you could use those from here if you wanted. I like this method for this particular one really well. So I can rewrite this as the sine of alpha over the cosine of alpha plus the sine of beta over the cosine of beta. That's the top. Fractions inside of fractions, it looks really yucky. I've got the bottom, and the bottom looks just like the top, but with subtraction, right? Just like the bottom with subtraction, top with subtraction. So I have sine of alpha over the cosine of alpha plus the sine, not plus, minus on this one, my bad, minus the sine of beta over the cosine of beta. Okay, did I get them all in there right? I mean, I didn't ask you if you liked what I saw, right? That's not the question. Are they all right? They're there, right? That's good, okay. It looks really awful. And there's more than one way to do this particular problem and to clean this up, but let me introduce or reintroduce, hopefully, a method for doing this that's really nice. When you have lots of little denominators and some of them match, which these do, right? I've got a cosine alpha denominator and I've got a cosine beta denominator, and I've got them in a couple of locations. One of the things that's really nice to do is to simply multiply by each of those denominators through the entire problem. So I'm going to show you two steps and you can decide which one makes sense for you to write down. So hold tight and you can just decide after this. I'm going to multiply by cosine of alpha, cosine of beta. And if you do it on the bottom of the denominator, you have to do it, if you do it on the bottom, you have to do it to the top. Cosine of alpha times the cosine of beta. And what we're going to do is we're going to distribute this through to each of these pieces. So you can draw it like this if you'd like. This is one option. Option number 2 is that you could write it like this instead. So instead of writing it the way I've done, is that you could write cosine alpha, cosine beta next to each of the 4 fractions. It's actually really nice, even though it's a little bit more writing, to write it that way. And let me show you why, and then it's your choice which one you do. Okay, did I get all the pieces in there? I think I did. If you've written it out, a little bit longer way of writing, what you'll notice is that there's some pieces that are going to cancel. And in particular, the pieces are every single denominator. And the reason that every single denominator cancels is because we chose specifically to multiply by the denominators. So on top, I now have these 2 pieces. So this is in whichever order you'd like. I'll write it just as they're showing up. So cosine of beta, sine of alpha, plus sine of beta, cosine of alpha. That's the entire numerator. In the denominator, I have the cosine of beta and the sine of alpha. Minus, and over here I have the sine of beta and the cosine of alpha. Now, it's not quite where we need it to be, right? We want it to match exactly what's on the left-hand side. The left-hand side actually expresses it in terms of single signs of addition pieces. So we need to verify that these actually do what we're expecting them to do. And if you flip back over and you take a look at them, the first, the numerator, is addition, okay? What that means is the order doesn't matter, and you know that to be true. 5 plus 2 is 2 plus 5. So I'm not terribly concerned if the addition is swapped around. Also, multiplication, these are called commutative properties, can be flipped, right? 5 times 2 is the same as 2 times 5. So try not to get hung up on the actual ordering of things when there's addition involved. So do you see a sine-cosine pair where there's addition? And you should. It should be the very first one that's listed, sine of alpha plus beta. And the alphas and the betas are both there. Sine is in one and cosine is in the other. Except for the ordering of things, because there's addition and multiplication, it in fact does match the sine of alpha plus beta. It's exactly what it is with that definition. The denominator is a little harder to actually say that with because there is subtraction, so we need to make sure the subtraction's in the right order, right? So I want to make sure that we have the subtraction piece. So if you look at this second one of those two, right, sine of alpha minus beta, it says it should have the sine of alpha and the cosine of beta. I do have those, sine of alpha and cosine of beta. They're switched. That's okay. It's multiplication. You can switch the order of multiplication and have the same value. And the same thing happens with the second pair. I have the sine of beta and I have the cosine of alpha, just like it has. It's switched, but the order doesn't matter because it's multiplication. So this is, in fact, the sine of alpha minus beta. And at that point, we see that it matches the other side that we never touched, and we can check it off and we're good to go. Okay?